relative speed, or what happens when there's more than one moving object. And when we dive into Einstein's theories of special and general relativity, one of the keys is going to be what we call relative motion. What happens when one object is moving relative to another. So right now, the person that you're sitting next to and you have a relative motion of 0. Einstein asked, what happens if one of you is moving? And what's the correct reference frame or point of view? Suppose you're driving down the freeway with your speedometer reading 100 kilometers per hour. When a Ferrari hurtles by you, its speedometer reads 180 kilometers per hour. And suppose a tow truck is parked at rest beside the freeway. Can I use F for Ferrari, T for tow truck, and Y for you? Okay. What would the tow truck see? And I wrote here, the velocity of u relative to the tow truck. That's way too much writing. I think we're going to write this as the velocity of u relative to the tow truck. So now you want to imagine you're sitting in the tow truck. If you look in your rear view mirror, you would see the headlights of your car getting closer and closer and closer. And then you would see the taillights receding. You would see the car go past you at 100 kilometers per hour magnitude, and you would translate that into positive or forwards because you saw the headlights in your rear view mirror get closer, and then you're seeing the taillights recede away from you. So we're going to argue that the tow truck sees you as that's kind of meh. What's the velocity of the Ferrari relative to the tow truck? Well, same argument. The tow truck sees the Ferrari go past at positive 100 kilometers per hour. That's the most common reference frame that all of us kind of think about. We typically measure stuff relative to an object sitting and traveling at the same speed as the ground, which is a fancy, longer way of saying what we call at rest. But now let's imagine we're in the car. What would we see? First of all, when the Ferrari goes past you, you don't see it traveling at 180 kilometers per hour. You would still see it in your rear view mirror and see the headlights getting closer. And then you, as it goes past you, you would see the taillights receding. So you would still call it positive. Oh, let's write this as the Ferrari relative to you. So you would still see it as positive. But how fast would it appear to be traveling relative to you? 80. I wrote down why, but can you kind of see why? It's a tough explanation, but I hope you can kind of see. Yeah, because I've already got 100 of those kilometers per hour taking care of myself. What about the tow truck? Well, here's what you actually see. When you look in front of you, you see the tail of the lights of the tow truck coming closer to you. And then when you go past it, you see the headlights moving away from you. Technically, as far as you're concerned, if you imagine that you are at rest, the tow truck is in reverse. So V tow truck relative to you, I'm going to argue you see it traveling backwards at 100 kilometers per hour if you imagine that you're standing still and the ground is spinning underneath your tires. Annika, you okay with that argument? Okay. What would the Ferrari see? Well, the velocity of u relative to the Ferrari, not 80. Yeah, it sees negative 80 because it sees your rear lights, tail lights coming towards it as though you were backing up, and then when it passes you, it sees your headlights receding in the distance. If it thinks that it's at rest, it sees you traveling, and it sees the tow truck traveling at negative 180. So the question Einstein asked is, which one of those is the correct view? Yes, they are all correct. It's all relative. This is why he called his theories relativity. There is no correct frame of reference. It is equally valid to say, for example, if you're on a train, you can say that the train is moving and the earth is at rest, but it's equally valid to say that your train is at rest and the earth is spinning underneath the wheels, slowly rotating underneath you. And you cannot come to a physics contradiction if you assume either one of those is correct. Either one of those will not lead to a contradiction, which means they are correct, both of them. Okay? I wrote here, Mr. Dewick, is there a short way to write this? I already showed you the abbrev. I'm not going to be too fussy with the negative and the positive. I'm going to be more concerned with the magnitude of the difference. We're going to do a couple here where we're still going to talk about negative and positive, and then we're just going to say, look, we're not interested in relative velocity. We're interested in relative speed. Who cares about the direction? So you perceive the Ferrari to be moving away at 180 kilometers per hour. Not at 180, but at 80. The relative velocity of any moving object depends on your point of view. The fancy term we talk about in physics is your reference frame, your frame of reference. If you actually take a course on relativity, almost every time you'll begin the question, okay, what's your reference frame? We have to define that before we can go any further. What's your zero? And it might be different from your zero. You might have noticed this if you've ever walked on one of those moving walkways at an airport, some of you nodding, where you look at the person who's, for some reason, not using the walkway, and it feels like if you think about it, they're walking backwards, even though their legs are moving forwards because you're passing them. Okay? Example 1. What is the velocity of the passenger train relative to the observer on the ground in each case? So I know this person is walking at 1.2 meters per second to the right. The train is moving at 15 meters per second to the right. What would the relative velocity, my abbrev for relative velocity is VREL, be here? 16.2. What about here? 13.8. By the way, and I'm glad Alessio made the sloppy mistake. You heard him, 14.8. On a test or a quiz, because I've forgotten to carry the one so often, I will type even basic math into my calculator. I may have said this to you before, but like I'll do 3 plus 2 on my calculator because the number of times I've made that dumb mistake drives me crazy, and I hate losing half marks for just a really silly or a sloppy mistake. Losing a half mark, only a half mark, would just drive me. Okay. Hey, question. Let's imagine that instead of a box car, it's a flat car train and the train is long. What if this person walked backwards at 15 meters per second? What would their relative velocity? Put your pencils down, look up. Well, to dial it in that accurately, it was almost always a little bit too much air pressure, and so the ball was still moving. Then they finally had it dialed in, and Grant couldn't time because he's kind of eyeballing the timing and the launch. And it's not like you've pressed the button right when you're in the right location. The circuit takes a while to activate, so you're estimating how long it takes to get to that location. Yeah. A zebra is running away at 50 kilometers per hour from a cheetah going at 90 kilometers per hour. What velocity does the zebra see the cheetah as having, and vice versa? Z for cheetah, So Z for zebra, C for cheetah. So what does the zebra see? First of all, what's the relative speed between these two? Not velocity. I don't care about negatives or positives. Okay. You can imagine that one of these is at rest and the other one is traveling at 40. The zebra, if he was wearing a rear view mirror, would see the front face of the cheetah getting closer and closer. So I'm going to argue that the velocity of the cheetah relative to the zebra is positive 40. The velocity of the cheetah relative to the zebra, well, if the cheetah imagines that it's at rest, it sees the hindquarters of the zebra coming closer and closer. As far as it's concerned, the zebra is moonwalking backwards. Strange, but yes, in physics, there's no, we have to make that argument. So, key idea is the relative speed is 40. Yeah. Oh, I wrote this wrong. Which one? Cheetah relative to the zebra. This should be zebra relative to the cheetah. Thank you, Candy. Okay. I like part C. If the zebra, I'll tell you when I like, but we'll get there. If the zebra starts out 90 meters ahead, how long will it take until the cheetah catches up? What's this question asking me to find? What's that 90? What are the units next to that 90? First of all, the units next to that 90 are meters. Oh, and what did we say that we're going to assume A is for this whole unit? So I know A is 0. What I'm going to use is the relative speed, but I've got to convert that to kilometers, from kilometers per hour into meters per second. Something to do with the 3.6. Yeah, more specific, can you actually tell me what the answer is? $11.1 repeating? Okay. Which equation? Is there an acceleration? What's the acceleration? So Alessio said, is V-rel VI or VF? What's the acceleration? So V relative is V initial, is V average, is V final, because the velocity or the speed not changing. So really, is V V? Yes, wherever there's a V, you can put 11.1 repeat. Which equation? Yeah. Half AT, except what's A? So it's going to be D equals VIT, except what's VI? VREL. Here's our modified special equation. When more than one object is moving at different speeds, we're just going to use that. Rather than look at each object and have them both moving. By the way, you can do that with a system of equations. It's doable. We're just going to say, let's let one of them be at rest, and let's use the relative speed. Much nicer. What? Alessio, what? You want to take option number 3? What are we trying to get by itself? Time. So we'll divide by V. So it's going to be 90 divided by 11.1 repeating. Use your answer button if you can. What'd you get? 8.1? Even? Oh, nice. Units? Okay. So, if safety for the zebra is 8.0 seconds away, zebra lives. If safety for the zebra is 8.2 seconds away, lunchtime. right? And you're kind of laughing a little bit, but watch wildlife videos. Herds of animals, they're doing this math. If you watch the wildlife video, the cheetah or the lion will be walking towards the herd is casual. The lion gets a bit closer, the herd is still casual. They know their relative velocity. Oop, now it's getting close enough that they're doing the calculus. They're looking at, okay, can I get away? What's my relative velocity? Now I'll start to run. But they don't want to run unnecessarily, because the animals that run unnecessarily are wasting energy. They'll get weeded out. The animals that are better at doing this, whether it's intuitive or whatever, that have a hard wire in their brain that can run these numbers, those are the ones who pass their genes on to the next generation. Cheetahs know this as well, because you'll watch them, they're walking, or lions, prey animals, they're very slow and casual as they slowly walk towards the herd, because they know if I start to run, I can't catch them. Safety's too far away before I catch them. And the zebras know that as well. Let's just both of us not waste the energy. That is the great circle of life, Simba, the great circle of life. Nick and Cole are having turn the page. Nick and Cole are having an argument at an airport on a windy day. Nick says the airplane should take off in the same direction as the wind. That way the wind pushes them from behind, so the plane will get a speed boost on the runway. Cole says, no, the airplane should take off into the wind. He's not really sure why, but it kind of makes sense to him. Who's correct? You know, let's vote. Once again, how high you hold your hand up is how sure you are of the answer. So we have our option. If we're an airplane, do we want to take off with a tailwind pushing us? That's option number 1. Or do we want to take off with the wind in our face? That's option number 2. Who says A, Mr. Dewitt? Get the tailwind. Option number 1, A. The first one. 1. Who says second option? The question really is, what makes a plane fly? Lift. What gives it lift? What? It's how fast it's traveling through the air. So let's suppose there's a 5 meter per second wind on my nose as an airplane. Even though I'm at rest relative to the ground, how fast am I already traveling through the air? 5 meters per second. Planes always take off and land into the wind, which is why you'll never see an airport without one of those windsocks, which is why for the really small community airports, you may have seen them if you're driving in the interior where the airport is just a field with a windsock. Watch a plane coming in, they'll buzz by low first. They're checking which way the windsock is blowing if they can't see it from up high, and then they'll turn and they'll make sure they're landing in the wind. So who is correct? Cole. In fact, you can sometimes have the wind moving fast enough that you have lift, even though your relative ground speed is 0. You're going to see somebody who made a very expensive mistake. So, what was the speed of the airplane in the video you just saw relative to the ground? What was the speed of the airplane relative to the wind? Takeoff speed. I don't know what, but for the rest of this lesson, we're going to concern ourselves with relative speed, not velocity, so don't worry about the negatives or positives. But acceleration will always equal what? Any time for the rest of the year we have 2 moving objects, we can assume A is 0. If we let A be 0, I can prove Einstein's special relativity to you using Math 8. If I bring in acceleration, that took Einstein 10 years of hard math, and it's well beyond my ability to handle. Every once in a while, I think to myself, I'll figure out general relativity, and I'll find an online textbook, and I get about a page in, and okay, that's why it took Einstein. Have a nice day. State the relative speed in each case. So here's two, let's pretend they're trains. They're each going 40 kilometers per hour. What's their relative speed? As far as they're concerned, they wouldn't see the distances changing at all between them. So as far as they're concerned, they are at rest, 0. What about the right-hand diagram, this one here? What's the relative speed between these two? How could you get that? I think if they're going in the same direction, bigger minus smaller. What about this third diagram? What's the relative speed? And I'm going to give you a hint. It's not 20. We said no negatives. George, this is why head-on collisions do so much more damage than a rear-ended collision. You'll notice the same speed as the previous diagram, but there, because their relative speed is 20, when you rear end, that's going to hurt. Here, so if you wanted to generalize same direction, usually bigger minus smaller will do it, unless it's a weird example. Opposite directions, usually add them up will get you your relative speed. I like example 5. I like example 5. Example 5 is a nice question. This is probably the stereotypical classic made-up algebra word problem. Whenever somebody talks about a math word problem, they start out something like this. A train leaves Chicago at 80 miles per hour. At the same time, a train leaves New York heading to Chicago. This is where you have two objects moving. And you can do this algebraically with a system of equations, or you can use relative speed. So here's two trains traveling in the same direction. How long does it take the back train to pass the front train? Here's my first argument. What do I mean by passing? To me, the back of the first long train has to get all the way past the front of that train. Now, I realize they're both moving. As far as I'm concerned, no, they're not. It's all relative. I'm going to use relative speed. What's the acceleration here, by the way, Owen? So I'm going to use d equals v rel t. I deliberately didn't put that on your green sheet because I think it's a reasonable derivation from d equals vit plus a half at squared. Max, you going to make it? You're not. What's this question asking me to find? You can write the rel each time if you want to, but I've clued in where I'm going and I'm organized but lazy. What's the total distance the back train has to cover? I think 150 plus 200 is what it's got to do to get past the front of the front train. What's the relative speed here? Please don't say 13. Please don't say 5. 8. Which is what? 31.5. That's a much nicer method than setting up a system of equations and solving for an x and a y. It's doable that way, but yeah. Okay? So here's the phrase you're going to hear me say very often. Are there two different objects traveling at different speeds? That's a job for relative cross-out velocity speed, because we're not going to worry about the negative positive. But you'll often hear me say velocity because I mix up speed and velocity out loud all the time because they both are v's. And just with that, we can do some kind of interesting questions. We can start to do a little bit of the physics of how radar guns work with police cars. And we can talk about airport design. Example 3. As you hurry to catch your flight at a local airport. Remember airports and travel? Oh, those were the days. Okay. You encounter a moving walkway that is 85 meters long It has a speed of 2.2 meters per second relative to the ground. Suppose you ignore the walkway and it takes you 68 seconds to cover that 85 meters at a constant speed. Oh, so what's A equal to, Owen? 0. What's your walking speed? Well, plus a half AT squared, but A is 0. How can I figure out how fast I'm walking? Going to be D over T. It's going to be 85 divided by 68. I don't think this is going to work out to a nice number. Might, but I doubt it. 85 divided by 68. Oh, holy smokes! So I'm walking at a lovely 1.25 meters per second. You know what? You're not speed walking, but you're brisk walking. Because that basically about that far every second. You're walking. Okay. First of all, how long will it take you to cover 85 meters on the walkway? Assume that you assume that you walk with the same speed on the walkway as you do on the ground. So now instead of walking the 85 on the ground, you're going to walk on the walkway. How long will it take you to cover that? I don't know. First of all, what's it asking you to find? Put your calculator down, Deegan. What's it asking us? Let's get organized. What's it asking us to find? What physics concept is how long will it take? Thank you. Is there more than one object moving at different speeds? The walkway and the person? This is a job for relative speed. So I'm going to make a little note here. D is still 85. I want VREL. What's my relative speed if I'm walking on the walkway? Well, what am I walking at? 1.25. What's the walkway moving at? How fast am I moving relative to the ground then? Yeah, and this is an exception because I said if both objects are moving at the same speed, you go bigger minus smaller. We're on the object. So it's not two separate objects moving at different speeds. We're on it. So it's going to be I walk at 1.25 plus the walkway is 2.2. I'll try doing this in my head. I think relative to the ground is at 3.45 meters per second. Okay. What equation? You know what? I looked at this one right up here and I said, I'll just imagine the rel sitting there, get the t by itself. Now, if you wanted to write d equals v rel t, go ahead. But yeah, I think it's going to be t equals d over v. It's going to be 85. And I get 24.6. How long did it take me without the walkway? What did I say earlier in the question? How long did it take me with the walkway? Just out of curiosity, how much time did I save? Do the math. Use your calculator. How much time did I save? I want a number. I want a number. Somebody needs to go 68 minus answer button. Were you really too lazy to do that? Okay. That right there is why they build the walkways. Please don't think that they build those walkways because you're tired coming off the plane. It's all about, can we get more people out of this airport faster? The more people we can get to their gates faster and on planes faster, that's money. And so they've run the numbers for these walkways and they've done the calculations and they've said, oh, if we have the person hit 8 of these in a row on the way to their gate, that saves them 4 minutes and 68 seconds. And that means in a day we can get an extra 592 passengers, and that's money. That's worth building the walkways. That's what that's the calculus that's going on behind this for airport design. What was that? Are you saying that I anticipated you with part B? Okay. So, folks, cross out the word U, put a capital A there and a capital A there. I'll let you try and figure out which student the capital letter A stands for, but we all know who it is, don't we? Okay? So, if once A gets on the walkway, A immediately turns around and starts walking in the opposite direction. First of all, what's his new speed relative to the ground? We're not going to worry about negatives and positives, first of all, okay? We're doing relative speed. So, the walkway is moving this way, how fast? Aiden is moving that way, how fast? 1 point. This is not a head-on collision where you add them together because you're on the walkway. What's the relative speed? Please do the math. Can someone do the math, please?
1.95.
Okay. Now, someone said negative. Relative to Aiden, he would call it, I guess, negative because he's moving backwards, technically. Okay? But we said for these questions, we're not going to worry about the negative or positive. We're just going to get the magnitude for now. Because now, how long would it take Aiden to cover? And by the way, if you're ever at an airport late at night and these walkways aren't crowded, have a little bit of fun with this. There's some beautiful physics going on there. How long would it take Aiden to cover the length now? So T equals D over V. It was still 85, but it's VREL, and now VREL is 0.95. 89.56. Rounded off properly?
Yes.
Okay.
That should take like 1 minute and a half.
For fun. Good physics. Okay. But the real, so Max said, why would anyone do this? The real question is, why would they build these walkways? It's purely for that right there. It's not because, oh, you're tired and we want to help it, make it easier for you to get out. It's airports are all about throughput, and especially after 9/11, which slowed everything down, they're looking for any excuse. You guys don't remember, before 9/11, we were just at the point where if my flight left at noon, I could show up at 11:50, check in at the curb, and walk onto my plane. That was what was happening at that time. Because the world after the millennium was all touchy-feely. After the year 2000, we were all hugs and kisses, and the 9/11 did change the world for the negative, okay? They were pushing for, because what does that mean? That means, again, we can get way more people through the airport. If they only got to show up 20 minutes ahead of time, we're packing them out, packing them in, shipping them off. That's money.
Ship them off.
Yeah. Because as soon as that plane's out, now another one's here. That's money. They're buying stuff in the airport. We're selling that airplane fuel. That's the money. We make no money at all while that plane is parked just sitting there.
Yeah.
I like example 4. I like example 4. Example 4 is a nice question. Police are in hot pursuit of a car which is 320 meters ahead, going 150 kilometers per hour. I already sense I'm going to have to do a unit conversion because I see meters and kilometers. If the police are going to ram the car in 20 seconds, what must their velocity be in kilometers per hour?
Over the speed.
What's this question asking me to find? Okay. Is there more than one object in this question? Are they moving at different speeds? This is a job for relative speed. What we are going to find is VREL. Let's look at what they gave us. What's that 320? What's that 20? You know what? That's meters and seconds. Those units I like. What's A? Could I find the relative speed that needs to exist for this to work out? How would I get VREL by itself? Oh, I'm so glad you folks are getting good at formula manipulation. So it's going to be 320 divided by 20. Pretty sure 16? Yes? That means the police have to be traveling 16 meters per second faster than the bad guys. How fast are the bad guys going? 150 kilometers per hour. So I think the next step, I'm going to convert this 16 to kilometers per hour. And then .208 is fine. So I said to you, this is a little, I teach you the physics of how radar guns work. A radar gun works in exactly the opposite of this. So the radar gun wants to try and get this speed, the 150. Sorry, people at YouTube can't see what I'm pointing at. Wants to try and get the 150, how fast the other car is traveling at. So it would know how fast the police car was traveling at. It would use a relative speed, and it would solve for this and give you a pretty good estimate of how fast the speed was. And again, it would be using a similar calculation. It's using how long it takes it to bounce back and return to. Actually, it's probably measuring a Doppler shift effect rather than how long it takes to bounce back, because that's so ridiculously fast with light. But it's a similar calculation. Short version. To calculate the relative speed between two different objects, if you're not standing on the sidewalk, if they're traveling in the same direction, bigger minus smaller, like the trains. If they're traveling in opposite directions, either towards each other or away from each other. Where that doesn't work is the moving sidewalk if you're standing on it. But I think you folks were okay in figuring out, oh, if I'm standing on it, I must be going faster relative to the ground. Add them up. If I'm Aiden walking backwards, I must be going slower relative to the ground. Add them up. Put your pencils down, look up. What's your homework? Owen, what can we assume A is for all of these? Okay. Number 2. Question number 2, what's the relative speed of those if they're heading towards each other? As a number, yeah, I think VREL is 16. And I think to pass each other, I think we're going to say the back of the first train has to get all the way past the back of the second train. I think D is 120 plus 260 plus 80. And I know they're both moving, but the nice thing about relative speed is we can ignore that, because that would make this way tougher to try and track. Who cares? It's all relative. Okay?
That's what they say.
4 is good. 5 is good. 6 is good. 7 is good. 8 is good. Skip 9. Or as I like to say, 9. 9. Oh. 10. 11. 12 is good. You can probably, if you write smallish, do your work right on here, but if you want to do it on a separate piece of paper, that's also fine. Probably 8, you know what, probably 4, 5, and 6, there's not really enough room. Where there's a picture, there's probably enough room, but that's relative speed. Okay? Next lesson, probably Monday, we're going to find out that there's one object in the universe that does not behave this way, that does not add speeds together.